And firstly, it is a public key encryption scheme. So there's a classical public key that everyone can use to encrypt, and the lessor holds the corresponding secret decryption key. The quantum aspect here is that this classical key can be encoded into a quantum state and sent to the lessee. And the lessee can use this quantum state to also be able to decrypt. The interesting part is that at a later point, the lessor can ask the lessee to delete this secret key. And at this point, the lessee can perform some measurement on the quantum state and send back a deletion certificate. So this proves deletion to the lessor. And the lessor can check that the certificate is valid. It's because the lessee can be malicious and can send some fake certificate. So if the certificate is actually valid, then it is guaranteed that the lessee has lost access to the secret key. This means if it now sees a new encrypted ciphertext, it will not have any idea about the underlying message. This is in contrast to the fact that earlier it had full ability to decrypt this ciphertext. But now that it has deleted it, it has no idea about the message. This primitive is enabled by the no cloning principle of quantum mechanics, which intuitively guarantees that unknown quantum states cannot be copied. And it is easy to see that it is impossible in the classical setting, because a lessee that gets a classical bit string instead of a quantum state can simply make a copy, which it can use to decrypt at a later point. Let's now see an application scenario for this primitive. Consider a streaming service like Netflix that has its data stored in some server, and it keeps this data in encrypted fashion. And the problem that it wants to solve is to send some trial period access to certain users. And it can do so by sending them a quantum decryption key, which they can then use to access the data. At a later point, the key can be returned and they can be compensated by something like a refund. Of course, one would expect there to be multiple users who would each need to get their own decryption key. And one would also naturally expect that if everyone is returning their keys, then they all lose access to the service. But this seemingly natural guarantee is not provided by the previous definition, where we only considered a single lessee that gets a single decryption key. And in fact, in this multi-user setting, the problem is that several users can collude, and they can try to learn something about the keys, which allows them to retain access even after deletion. So if there is now the stronger guarantee, not working somehow. Yeah, thanks. So now if there's a stronger guarantee that if everyone deletes their keys, then they all lose access to the service, then we call this scheme to be collusion resistant. And this is essentially the focus of this talk. And specifically, we'll be focusing on unbounded collusion resistance, where the parameters of the scheme scale polylogarithmically with the number of users. In contrast, in bounded collusion resistance, these parameters can scale linearly with the number of users. In the last couple of years, there have been several constructions of PKSQL from different standard assumptions. And the common theme here is that they're all completely broken in the setting of collusion. The reason for this is that they are defeated by a simple class of attacks where an adversary can get multiple decryption keys and then learn some crucial classical information by correlating these keys. And this classical information allows it to decrypt at a later point. And the most important fact is that the adversary can do all of this without disturbing any of the quantum state, which allows it to perform deletion in the usual manner. And the deletion checks would be verified successfully by the lessor. And this hints at the real challenge in this setting. And in fact, provable security is even more difficult to obtain. These previous schemes are defeated by a simple class of attacks, but one can consider some heuristic schemes that don't run into the simple attack, but it's not clear if more complex attacks won't be applicable to those. There are, in fact, some bounded and unbounded collusion-resistant constructions in the literature. But the problem with the bounded case, as I mentioned in the last slide, is that the parameters scale linearly with the number of users. And this can be quite inefficient. And the current unbounded constructions we have rely on strong assumptions like functional encryption and I/O. And the problem is that these are not even known to be possible in the post-quantum setting as of yet. So in this work, we first examine what collusion resistance means in the context of PKSKL. And we define this primitive called PKCRSKL, and CR stands for collusion resistant. And we show how to construct this primitive from the standard learning with errors assumption. We also consider an attribute-based encryption variant of this primitive. And we show that this can also be obtained from LWE. The construction uses several building blocks, but a key building block is a secret key variant of this target primitive, which we define and construct as well. Our main construction has quantum deletion certificates, but it's more desirable to have classical certificates. And we achieve this using a different construction from a stronger multi-input ABE primitive, which is still believed to be weaker than functional encryption and I/O. So in a bit more detail, the main result is the construction of this collusion-resistant variant of PKSKL from 3 building blocks. The first is the secret key variant of this primitive, which is also a quantum one. And the other 2 primitives are classical crypto primitives of lockable obfuscation and attribute-based encryption. And these are well-known classical primitives. And the nice thing is all of them can be obtained from the standard learning with errors assumption. Now, let me tell you briefly about what these collusion-resistant notions are. So consider a security game where the lessor is the challenger and the lessee is the adversary. And the lessee can request an unbounded number of decryption keys from the lessor. Later, it needs to provide deletion certificates for all of them. And if all of the certificates are verified correctly, then it is guaranteed that the adversary cannot distinguish ciphertexts anymore. In the paper, we have a more nuanced definition that incorporates a verification oracle, but the one here also gives the essence of the definition. So this is the public key primitive, but the secret key primitive is defined very similarly, except now there, of course, is no public key, and the encryption is going to be done with the secret key. The crucial difference in the security game for the secret key primitive is that the adversary does not see any ciphertext until it deletes its key. So the first time it sees a ciphertext is only in the challenge phase. And this makes it much easier for us to construct the secret key primitive, and we are able to obtain it from one-way function. So the core technical bulk is to upgrade the secret key variant into the public key one. And to do this, we leverage a classical crypto primitive called attribute-based encryption, which generalizes the notion of public key encryption. So here, there's a master secret key that allows to generate secret keys for different attributes. So here I've indicated them with different colors. And at the time of encryption, one can specify some policy that provides tailor-made access. For example, the policy can say that only the non-blue keys are allowed to decrypt. So here the green and yellow players would have no problem decrypting. But even if the blue players collude, they don't have any idea about the message. In fact, in this work, we require a quantum secure variant of ABE, which is secure even if the adversary receives an exponential superposition of secret key. And we're able to show that a well-known LWE-based ABE scheme satisfies this stronger property. So now equipped with this ABE scheme, we show how to upgrade the secret key primitive into the public key one. So this is how we do that. So consider the quantum decryption key of the secret key primitive, which I've written out as a quantum superposition here. And we actually require another property from the secret key primitive called the classical decryption property. So roughly, the property states that there's a classical decryption algorithm that can decrypt ciphertext of the secret key primitive using any term that appears in the superposition of the quantum decryption key. Now, the quantum decryption key of the public key primitive is constructed as follows, where we built on top of the decryption key for the secret key primitive, and on a new register, we construct the corresponding ABE secret key. So for the blue term here, we compute the ABE secret key for the blue attribute. And the encryption algorithm is going to use the encryption of ABE. And recall that ABE allows us to specify a policy. And our scheme will make use of a very specific policy. So particularly, the policy will contain an encryption of the secret key primitive, a ciphertext of the secret key primitive, which encrypts some dummy value like 0. This is actually a bit of a caveat I'll mention soon. But the main idea is that an ABE secret key satisfies the policy as long as its attribute decrypts the ciphertext inside this policy to 0. This may be a little bit technical, but the main takeaway is that this classical decryption property, along with the way the policy is defined, ensures that every ABE secret key the adversary is provided in this quantum superposition satisfies the policy. And this means by the correctness of ABE, the adversary is, or the lessee is able to decrypt the message. And it can, in fact, do so without disturbing the quantum state. Now, this might look like a convoluted way of constructing PKE-SKL. But to see why this is useful, observe what happens when the policy contains an encryption of some other value, like 1, instead of 0. So now, based on the classical decryption property and the way the policy is defined, all of the keys that the adversary is provided, all of the ABE secret keys, are actually useless in this hybrid. This is because the attributes of the ABE secret keys will decrypt the ciphertext inside the policy to 1 instead of 0 as the policy requires. So all of the ABE secret keys do not satisfy the policy in this world. And this means by the security of ABE, the message is completely hidden from the adversary. Now, the world with the encryption of 0 is what I've mentioned as the one that the construction uses, and it provides the correctness guarantee. And now I'm saying that there's this other world which has this encryption of 1, and this one hides the message from the adversary. So now there's currently no relation between these two worlds. And our main idea is that we can relate these two by invoking the deletion guarantee. So for deletion, we basically ask the adversary to return back the quantum decryption key, and this is where we actually require the deletion certificates to be quantum. And of course, we have to perform verification because the adversary can send some fake certificate. So for verification, we simply uncompute the ABE secret keys and verify the underlying secret key primitive's decryption key that is obtained using the verification procedure for the secret key primitive. So what all of this is essentially doing is that it ensures that an adversary that is deleting its keys is also deleting the underlying secret key primitive decryption keys. This means from the security of the secret key primitive, the adversary cannot tell ciphertext of the secret key primitive apart. So whether this challenge ciphertext is generated using a policy that contains this encryption of 1, or whether the policy contains the encryption of 0, the adversary cannot distinguish these two because it has deleted its keys. And because in the world on the right, the message is hidden by the security of ABE, the same applies to the world on the left as well. Now, at this point, we're almost done, except there's one problem, which is that the policy cannot actually contain an encryption of a secret key encryption scheme because we actually require public key encryption. To solve this part, we actually use a dummy policy in the actual construction. And we switch to the policy in the middle in the security proof using the security of lockable obfuscation. And that is all I have for today. Thank you so much.
Any questions? Quick question. Are you able to achieve adaptive security for your ABE?
No, we consider just selective security.
Okay, so are there any fundamental barriers for achieving adaptive?
I'm sorry, could you
I'm here.
raise your hand?
I'm here. Here.
Oh, I'm so sorry.
Are there any fundamental barriers to achieving an adaptive security? Let's say if we, instead of doing ABE secret key using, what if we do IBE based?
Right. I think for IBE, we can achieve adaptive security. But for ABE, I believe we would need at least sub-exponential LWE because ABE needs the complexity leveraging.
I see. So you can't do this from plain LWE, but say sub-exponential LWE, you could be able to do that?
I believe so, but we haven't analyzed the ABE.
Okay, thank you so much.
Yeah, thank you.
Let's thank the speaker again. All right, next up, we have Mahesh Srikumar Rajasri, and Mahesh will be giving us a note on adaptive security in hierarchical identity-based encryption. This is a work by Rishabh Goyal, Venkata Kopula, and Mahesh. Just take it away.
Thank you for the introduction. Hi, everyone. I'm Mahesh, and I'll be talking about our work on adaptive security in HIBE. This is a joint work with Rishabh Goyal and Venkata Kapula. So an identity-based encryption scheme is a notion of public key encryption where any string such as name or email address can be used as a public key for the user. So in many practical systems, entities are organized hierarchically. So in such systems, we would require that the higher level authorities to delegate keys to lower level entities. This motivates hierarchical IBE, a notion of identity-based encryption where it enables delegation across identity. There are 5 algorithms for an HIBE scheme. The setup which generates the master public key and the master secret key. The key generation algorithm uses the master secret key to generate a secret key for any identity. The encryption algorithm uses the master public key and an identity to encrypt a message M. Decryption uses an appropriate secret key to decrypt the ciphertext. And finally, the delegate, it allows any secret key holder to generate keys for any identity below them in the hierarchical tree. In this talk, we will consider identities as binary strings, and the hierarchy is defined by the prefix relationship, again, among these strings. One natural way to define HIBE security is as follows. The challenger runs a set of algorithm, and the adversary is allowed to request for keys for any identities unless they are not a prefix of the challenge identity. Then the challenger encrypts one of the two messages that is given by the adversary. After further key queries, the adversary must guess which message was encrypted. At first glance, this seems to be a reasonable security notion. However, it is fundamentally flawed. Why? This is because there's no delegation functionality in the security notion. Moreover, one can build an HIB scheme that satisfies this security notion from any adaptive IBE as follows. For setup, we run the IBE setup algorithm for each level in the hierarchy. To generate a secret key at the ith level, we invoke the IBE keygen algorithm for using the master secret key at that level. And to perform encryption, we invoke the IBE encryption algorithm independently for each prefix of the identity, but for the same message. And delegate, what it does is, it just simply returns the input parent secret key. Now, one can verify that the scheme is secure with respect to this definition, but it's completely broken if the adversary is allowed to get delegated keys. Now, the following security notion, which was introduced by Xie and Waters, captures the wide range of HIB attacks. And the difference in this security notion is that the adversary is allowed to make three different types of queries, key queries. The first one is initialize, where the challenger runs the key generation algorithm using the master secret key on the given identity, but it does not reveal the secret key. So this query captures like honest users being generated in the system. The next is delegate, where given an already initialized identity and a child identity, challenger runs the delegate algorithm to generate the child identity's secret key. Again, no secret key is released over here. And this allows the adversary to initialize more users deep in the hierarchy. And finally, we have the corrupt, where the secret key is revealed. And this can be any secret key that is generated via initialization or delegation, but it should not be a prefix of the challenge identity. Now, most of the initial constructions of HIBE satisfied a weaker notion of security called the selective security, where the adversary must commit to the challenge identity at the beginning of the game. Unlike in the adaptive setting, where it can give the challenge identity after seeing many key queries. Most of the initial constructions of selective secure HIBE were based on bilinear pairings, and most of them required the random oracle model. Later, they were extended to the standard model, and also you could build them from lattices and traditional groups. A major breakthrough came around in 2017 with Dotley and Gerg, who showed that we can construct selective secure IBE from any selective secure IBE, selective secure HIBE from any selective secure IBE. Now, using this framework, we can build selective HIBE from QR, LPN, and code-based cryptography. Whereas in adaptive HIBE, there is far less diversity. Non-constructions relied on bilinear pairings or lattices, and some of them requires random oracle model. Now, despite various heuristic attempts, building adaptive secure HIBE seems challenging. This is because proving adaptive security in HIBE is notoriously hard. In fact, Luco and Waters, and more recently, Brakerski, Medina showed that natural proof strategies break down when you consider delegation or like ABE. So this made it unclear whether we can construct or whether it's possible to construct adaptive secure HIBE without relying on random oracle models or strong algebraic assumptions. So to concretely understand why adaptive security is difficult, let's see how an adversary might attack in reality. The adversary can ask the challenger to start by initializing the identity 1, and then initialize identity 1, and then ask to delegate from 1 to 110, hence the blue coloring. Then it might corrupt 110, corrupt 11. Importantly, corrupting a parent node implies that you corrupt the entire subtree. Then it might move to the next subtree, initialize 0, delegate, ask to delegate 0, 1, corrupt it, 0, 0, initialize 0, 0, sorry, delegate 0, 0, and then decide to make the user 1 as the challenge ID. And then still you can perform more queries. So this flexibility to initialize, delegate, corrupt anywhere in the hierarchical tree is what makes this adaptive security pretty hard. The adversary can force the challenger to initialize and then delegate, but the challenger does not know which identity will become the challenge in the future. For example, okay, I think animation is not working. When 110 was delegated from 1 and then later corrupted, the challenger does not know whether 1 would become the challenge identity or will it get corrupted. If it gets corrupted, then the keys of 110 should be consistent with the keys of 1. If it becomes the challenge identity, then too much information in 110 might break the semantic security. So what we show is, assuming a selective secure IBE, we can construct an adaptively secure HIB scheme. This construction bypasses the previous HIB barriers through non-black box construction. We also extend this result to anonymous HIB, where we show that assuming the hardness of CDH or LWE, we can construct an adaptively secure HIB scheme that hides the recipient's identity, hence called anonymous. So let us now review the Dotlinger construction that builds selectively secure HIB, and this forms the foundation of our result. The construction requires 3 building blocks: delegatable PRF, garbled schemes, and selective secure IBE. In their original work, the authors used a primitive called OTSE, which can be built from selective secure IBE. For the sake of this presentation, we will stick with selective IBE for simplicity. A delegatable PRF is a PRF that enables delegation. That is, given a prefix, we can constrain a constraint key that behaves like the original key, but only on prefixes that extend, only on strings that extend that prefix. For the sake of simplicity, we'll assume that the order of delegation does not matter. Selective security says that for a fixed target, the evaluations of all the prefixes of the target point is indistinguishable from truly random string, even if the adversary is allowed to make evaluation queries and delegation queries outside this prefix chain. Now, a garbling scheme takes as input a Boolean circuit and outputs a garbled circuit, which can be evaluated on using a bunch of labels. Correctness says that the output of a garbled circuit is the same as the output of the original circuit or any input X. And security ensures that the garbled circuit, along with a bunch of labels associated with any input X, reveals C of X and nothing more. Let us now look at the setup algorithm of DG17 construction. The master secret key of the scheme is the key for the delegatable PRF. Using this key, we can deterministically associate each node in the hierarchical tree with an IBE master public key and master secret key by just running the PRF. Now, the master public key of the root node becomes the master public key of the HIB scheme. Let us look at how to generate a key for the identity 10. The key generation algorithm proceeds via the path from the root to the target identity node. For each level, it runs the key generation algorithm using the master secret key of the parent node for some encoding of the child node. And this encoding contains 2 bits of information, or 2 parts of information. The first is the direction bit, that is whether the child is a left child or the right child, and the values of the master public key of the child node. Now, this process continues until we reach the target identity node, where we have to generate another IBE secret key with respect to the dummy identity epsilon. Note that until this point, we can generate all the keys just using the key of the delegatable PRF. So to enable delegation, we have to generate a delegated PRF keys at this node. Now let us look at the encryption algorithm DG70. Recall that the public key of this HIB scheme is the public key of the root node. The encryption algorithm uses 2 circuits. The first circuit is T circuit, which has the message hard-coded in it, and takes as input the master public key and outputs an encryption of the message under the dummy identity epsilon. The second circuit is the B circuit, which has a bit beta and a bunch of labels hard-coded in it. It takes as input a master public key and outputs independent encryptions of the labels according to the bit beta and IB. Let us now see how to encrypt a message with respect to the identity 10. We first garble the TM circuit, and you get the garbled circuit along with labels. These labels are then hard-coded into a P circuit with the last bit of the identity, which in our case is 0. Repeat the process. Garble it, get the labels, hard-code it into another P circuit with the next bit of the identity, which is 1. Garble it again. Now, what you do is, your final ciphertext is the labels of the last garbled circuit associated with the master public key, hence the MPK epsilon I, and then all the garbled circuit generated during this process. Now that we understand how encryption works, let's see how decryption proceeds. The decryption algorithm first evaluates the Q tilde's garbled circuit on the labels. Now, this will produce an encryption of the labels for the next garbled circuit And you can decrypt this using the first set of keys. Now, decrypting these, you can only decrypt half of these labels, and then you get labels associated with the master public key next node, which is node 1. You repeat the process. Use these labels to evaluate the P tilde garbled circuit. You get a bunch of encryptions. Decrypt half of them to get labels associated with the next node, master public key of the next node. Evaluate T tilde circuit. You get an encryption of M with respect to the dummy identity epsilon, and use the last secret key to decrypt it. Now, the DG17 construction is the proof follows as proof is as follows. Since the adversary commits to the challenge identity in the beginning, you can replace all the PRF evaluation from the root node to the target node, challenge node, to truly random string. Then you can use the security of the GC garbled circuit to replace the labels and the garbled circuit. And you can then change the IB ciphertext, half of the IB ciphertext, to encryptions of 0. You can follow a similar template to replace all the entities in your ciphertext and make it completely simulatable. Finally, the security follows from the security of the IB scheme. Now, the challenges of the adaptive security is that the DG17 is selective because we have to selectively puncture the GGM tree at the target identity or the challenge identity, and this is required to build selectively secure IBE, selectively secure delegatable PRF. So you can ask, why not use adaptive secure delegatable PRF? For a long time, we didn't have such constructions. Recently, Hoffheim, Kastner, and Klein built one using clever rewinding technique. This sparked our hopes. What if we can use these techniques to build a delegatable HIB, or at least come up with new proof strategies? So what we show is indeed adaptively delegatable PRF is enough to show DG17 is adaptively secure. Interestingly, the construction does not require any changes. And this might be the reason why the DG17 template hasn't seen any structural improvement in the past few years. The construction was enough. But you might think that, okay, what if the proof might be the same? Just put in the delegatable PRF proof into it, but this does not work. We have to consider the adaptive adversary is very challenging. So those things need to be kept in mind while proving the security of the DG17. So again, the DG17 fails for adaptive setting because in the selective settings, we have to hardware each of the garbled circuit, but you can do that only if you know the challenge identity ID star. But in the adaptive setting, you don't know the ID star in the pre-challenge phase. So the step-by-step simulation of the garbled circuit fails because you had to guess all the prefixes in the pre-challenge phase. And this is why we need a new proof. And we use nested hybrid arguments and pebbling style strategies to overcome these difficulties. So in our proof, we start from a regular HIB security, then move to a hybrid where all the secret keys are generated using the master secret key only. You can achieve this by using an additional PRF key, which makes the key generation algorithm and delegation algorithm the same. Then in the ith hybrid game, we simulate the first I garbled circuit. And the final game, we simulate all the garbled circuit, including the one that encrypts the message. Finally, the security follows from the underlying IB. Even though this outline mirrors the structure of the DG17 proof, the proof in the intermediate steps is different. So in the ith step, what we do is we first garble the ith garbled circuit. Then we replace the PRF evaluation with a truly random string. And then we use the IBE security to switch half of the ciphertext to an encryption of 0. But again, the problem over here is we don't know ID star yet in the pre-challenge phase. So to kind of handle this, what we do is we add an additional hybrid where we revert back to the PRF evaluation. So this enables us to just make one guess at any given point of time. This style of pebbling style argument has been done in other works, including one for adaptive garbled circuit. But even with this single guess, there is an issue because the probability of success probability become negligible as I grows. To handle this, we use a nested hybrid argument that depends on the first query that overlaps with the prefix of ID star. And since the number of key queries are polynomial, this happens with very good probability. Sorry. And we also use the same techniques in our anonymous HIB construction also. So to conclude, we show that adaptively secure HIB can be achieved from selective IBE. So the construction was already there. All that was required is a new proof. As open problems, we can ask to whether we can get tighter security laws. Or can we get like, practically efficient construction that avoids garbling schemes? Another interesting question is whether you can use these techniques in other delegatable systems. Concurrent work by Goyal and Yodagiri constructed delegatable ABs from stronger assumptions, thus highlighting the interest in adding delegations to more advanced cryptographic primitives. With this, I end my talk. I'll be happy to take questions. Thank you.
Thank you, Mahesh, for the talk. Any questions? So could you expand a little bit on your second result for the full anonymity? Do you use the same trick, or do you need any additional tricks?
It's almost the same tricks, because there was work by Brakowski et al. Which build anonymous ABE, and they use again similar DG17 template.
So pretty much just apply the same proof technique and
the proof techniques has to be like handled in this way, but it's almost
technique. Yeah, I see. Okay, thank you. All right, let's thank Mahesh again. All right, so next we have a combined talk of two papers. So the first paper is Registered ABE and Adaptively Secure Broadcast Encryption from Succinct LWE by Jeffrey Champion, Jiaxin Guan, and David Wu. And the second paper is Unbounded Distributed Broadcast Encryption and Registered ABE from Succinct LWE by Ho-Tech Wei and David Wu. Jeffrey will be giving the talk for both papers.
Oops. This is working.
Let's welcome Jeffrey.
First in clicker. Oh, it's this. Okay. Fine. Okay. All right. Hi, I'm Jeff, and today I'm going to be talking to you about these two papers on the screen, one by myself, Yaoqing and David, and another by Ho-Tech and David. And so the focus of this talk is going to be on new techniques for constructing registered ABE and broadcast encryption from the succinct LWE assumption. Specifically, we're going to be considering the distributed variant of broadcast encryption, where in this setting, each user is going to generate a public key pair, public key and a secret key, and publish the public key to some public key directory. And we want the property that basically any user can come along and generate a ciphertext to a subset of these users, such that users in the set can decrypt, and users outside the set learn nothing about the message. And to make this non-trivial, we want to require that the size of the ciphertext is independent of the size of the set. So a little more formally, you can imagine that there's some public parameters generated by some setup algorithm, and keygen will depend on these public parameters, and encryption and decryption will both depend on the public keys in the set. And note that this implies the traditional notion of broadcast encryption by simply concatenating all of the public parameters and the public keys together into a long master public key. Okay, so this is an interesting primitive in itself, but we could also consider the extension to more general functionalities, and we consider this notion of distributed attribute-based encryption, where here, now public keys and secret keys are associated with a function fi, or a policy, and ciphertexts are associated with a public attribute X. And we want the property that a secret key for Fi recovers M if and only if Fi of X is equal to 0. And on the other hand, we want that users with Fi of X equal to 1 learn nothing about the message M. Here we're reversing the convention a little bit because it will be helpful when working with lattices. Okay, so this is a natural generalization of the previous primitive. However, if we're reusing the same set of users over and over again, this is a little bit unsatisfying because encryption and decryption scale linearly with the number of users. And so we might want some sort of pre-processing phase. And this is exactly the notion of registered ABE, where we now have an aggregation algorithm which takes in a bunch of public keys and aggregates them into a small master public key along with small hints. And so now encryption and decryption can run in time, which is independent of the number of users. Okay, so now that we have the two notions we're going to be talking about, let's see what's been done previously. So on the registered ABE side, we can get constructions for all circuits without any limitations from indistinguishability obfuscation and witness encryption. And then from pairing-based assumptions, we can get a more limited construction, which works for NC1 circuits, but has a structured setup and a priori bound on the number of users before setup time. On the distributed broadcast encryption side, we can get more constructions from pairings with the same limitations. And we can also get a construction from the succinct LWE assumption, which is a lattice assumption. And here, we have the same limitations as the pairing constructions, except we also are limited to selective security, which we cannot generically upgrade to adaptive. And so the question that we ask in this work is, how far can we push these lattice assumptions? And so here's what we show. On the distributed broadcast encryption side, we show CHW shows how to get adaptively secure DB for bounded number of users from succinct LWE in the random oracle model with quadratic public parameters, linear public key size, and constant everything else. Dub25 shows how to get selectively secure DB for unbounded users from succinct LWE. And this can also be made to have a transparent setup using this newly introduced decomposed LWE assumption. And note that this is the first scheme with unbounded users without or transparent setup without obfuscation or witness encryption. Okay, so on the registered ABE side, CHW shows the first registered ABE scheme for all circuits from the same assumptions as the previous slide and with similar parameters without obfuscation or witness encryption. And Dub25 again extends this to unbounded users and potentially transparent setup. Okay, so this is what we show. And yeah, additionally, in the registered ABE case, we also get ciphertexts with only depend on the depth of the circuit, which is something we don't even know how to do from witness encryption. We actually only know how to do this from obfuscation. Okay, so these are our results. And before I get into the technical part of the talk, I just want to say, like, what are sort of the key challenges that we have to overcome to construct these registered ABE systems? So the first is functionality, where we want to succinctly aggregate a bunch of public keys in a way that enables for correctness. And the second is security, where we want to simulate a challenge ciphertext where the public keys are adversarially chosen. And so if it's not really clear what that means, in the lattice setting, you can sort of imagine that we have some ciphertext component, which is an LW sample for matrix M, and potentially the matrix M here could be adversarially chosen. And so kind of what these works are about is how to sort of overcome this type of issue, because if a matrix is adversarially chosen, we cannot hope to show that this LW sample is uniform. Okay, so now let's get into this assumption that we've been talking about. So this is more of like a family of assumptions. And it basically says that LW holds with respect to a matrix A, given a trapdoor for a matrix which is related to A. In particular, it has A along the diagonal and these U1 through UL stacked on top of each other. There's several instantiations in the literature, sort of all weaker than the previous one. Maybe the simplest one to describe is what we usually call succinct LWE, where A is uniform and UIs are uniform. But this newly introduced decomposed LWE assumption allows us to make A structured, but now the trapdoor is actually public. And so What this means is that it's actually becomes very easy to get something like transparent setup using this assumption. Okay, but if we use this assumption as is in this talk, it's going to be a lot of algebra. And so to try and abstract some of that away, we're going to use this abstraction of a matrix commitment introduced by Wee. And you can sort of think of this as like a vector commitment to vectors, where we basically just have a commit algorithm that takes in some public parameters and a bunch of vectors M1 through ML, outputs a fixed size commitment C, along with openings Z1 through ZL. And this can be a deterministic or randomized procedure. The opening relation says that for all I in L, C times Vi, which is a low norm vector, is equal to Mi minus A times Zi, where Zi is the opening, which is also low norm. And you can think of the public parameters as describing these VIs along with the matrix A. And this is just a correctness property. The only security property that we require is that LW holds with respect to A, given the public parameters. And so basically, we can instantiate this type of thing from any of the succinct LW family of assumptions. Okay, so now that we have this under our belt, let's go ahead and jump into the constructions. I'll start with a high-level approach, and we'll start with the DBE construction. So the way it's going to work is each user is just going to generate a dual regev public key secret key pair and publish the public key. So that's keygen, very straightforward. Then what encryption is going to do is Merkle hash all of the public keys of users in the set by the matrix commitment, which you can think of as like an algebraic Merkle hash. And then we're going to encrypt with respect to the hash using dual regev encryption in such a way that a user I and S can use the local opening for the hash at position I to derive an encryption of the message under their public key and just decrypt using their secret key. So this is a very simple approach and actually can be viewed as kind of like an algebraic instantiation of the witness encryption idea. Okay, so let's see how this actually works. So, okay, the public parameters are going to be public parameters for the commitment, which includes A and VI. Note that these are going to be fixed size with the right instantiation. In addition, there's going to be a uniform vector P. The public key for each user is just going to consist of matrix A times some short sort of like 0, 1 vector yi. You can think of it like this. And the public key is just going to be this product, which we'll call Ti for short. So how do we encrypt to a set S? First, we're going to have a message blinding component, which will be LW secret S times a vector P, which you can think of for the sake of this talk as the message itself. Then we're going to have a commitment component where we basically commit to P plus Tj at position J if J is in the set, and we commit to 0 otherwise. So it's like we have a huge collection of vectors, and the ones at the position J are going to be 0 if they are not in the set. And note that because there's only going to be a polynomial number of public keys, we can efficiently do this. Okay, and then the last component is just going to be a component to help with decryption, which will be an LW sample for A. And that's actually it. So note that just by definition of the commitment we created, we have that for all I and S, CS times VI is equal to P plus TI minus A minus Z times A times ZI. And note that VI and ZI are public and low norm. And so what this means is that this equation will hold even if CS and A are LWE samples. So this will approximately hold. And just by rearranging the terms, what do we get? We get a public way to derive an approximation of a dual regev ciphertext under PKI. And so now a user can just decrypt by multiplying S times A by YI and then subtracting to get S times P. All right, so this is the whole DBE construction. I'm not going to talk about security, but this is a small edit distance away from something which is actually secure. Okay, so now let's see how we would actually extend this to a registered ABE scheme. So the idea is we're going to change our outline a little bit. First way we're going to change it is in key generation, we're going to combine the public key with the function encoding. And then at aggregation time, we're just going to commit to all registered users or hash all registered users and publish this hash as the master public key. And then encryption is also going to provide a policy check, which depends on the attribute. Now, decryption will sort of follow in a similar way, where now we can derive an encryption under the combined public key, and we'll only be able to decrypt, only be able to sort of like complete your secret key if the policy check passes. So this is kind of exactly what we want to do. But a few things I left vague here, and that's kind of on purpose. So what is this function encoding and what are these policy checks? So for that, we'll need a little bit more background. So specifically, we're going to be using this lattice-based homomorphism, which basically says the following. Given an input x and a function f, as well as a matrix B, there exists a low norm matrix H such that the following holds. Basically, if we take an encoding of x with respect to B, we have a low norm mapping from that to an encoding of f of x with respect to B sub f, where B sub f is some matrix that depends on B and f. And this matrix G that you see is just some sort of public gadget matrix. It's not too important exactly what it is, but all you need to know is that it's easy to find a low norm x such that G times x is equal to any vector D of your choosing. And so using this type of operation, which we'll call G inverse of D, we can multiply both sides and vectorize this equation. And so this is the form that we're going to be using. Okay, so with this, we can now describe the registered AB scheme. So how does it look? So we're going to start with the distributed broadcast encryption scheme and change it in a couple ways. First way we're going to change it is change this commitment to basically broadcast to all registered users and set the master public key to be this commitment or hash, however you want to think of it. And the second change we're going to make is we're going to put in this policy check, which is basically an LWE sample of the encoding of X with respect to B. And note that this grows with L, but we can actually compress this via more matrix commitment technique. And we also put B in the public parameters. But this too can be compressed. Okay, so how do the public keys change? We basically are going to take the previous public key and add this B sub fi comma di, where di is going to be some random vector in the public parameters for each user. So in the unbounded case, we'll want to derive this from a random oracle. But basically, each user has sort of like a unique thing, unique function encoding that depends on their unique PI. And so to sort of enforce this, we're going to need non-interactive zero-knowledge proof of knowledge of the secret key as well. Okay, and I claim at this point we kind of have the exact invariant that we want, because recall that we have a low norm vector H that will map S times the encoding of X with respect to B to S times B sub fi comma di, as long as fi of X is equal to 0. And otherwise, you'll have this S times di term, which you don't know how to cancel out. And so what this gives us is basically a user can only complete their secret key and get S times ti if they pass the policy and are also registered. And so using this invariant, we have correctness exactly as before. Basically, we just do the exact same thing, and now we just have a different way to cancel this S times t term and get S times b. Okay, so this is all for the basic functionality of the scheme. So now let's get into how you actually might try to prove security of this thing. So we're going to be considering the notion of attribute selective security, where the adversary fixes an attribute, and the challenger is going to then generate the public parameters. So in the registered ABE setting, the adversary can query for honest users associated with some function f and get the public key in return. And then at some point later in the game, it makes an aggregation query where it can choose its own public keys and also mix those in with honest public keys if it wants to. And so basically what we require is that if a key is adversarial, it cannot trivially decrypt. Basically, it shouldn't be able to satisfy the policy. And at this point, it's just semantic security, where the challenger is going to generate an encryption under the master public key, which it aggregates, and then encrypt to a random bit. Adversary has to guess the bit. Okay, so basically the sort of the tricky part of this security game is going to be simulating this final encryption here. We're not really going to go over exactly what happens with all the public keys and stuff. So let's see how something like this might work here. So what do we know? We know that from commitment security, we have LWE hardness for S times A, even given the public parameters of the commitment. And so what we want to do is take this LWE sample for A and use it to generate the rest of the ciphertext components. So what's good for us is that P and B are both going to be uniformly random matrices and vectors. And so we can set these to be A times some low norm vector in such a way that we can generate their ciphertext components just from S times A. So that's good. But as I alluded to before, this S times CL term is going to be a serious thorn in our side because we are committing to vectors which are adversarially chosen, and thus this matrix CL is an adversarially chosen matrix which we want to prove is uniformly random. And so this is just not going to happen as written. And so what are we going to do to get control back from the adversary? Well, we're going to try and re-randomize it. So the idea is to take a randomized commitment to the all zeros, bunch of zero vectors, and just add it to C all. And yeah, this seems like a reasonable way to do things. However, it kind of leads to a domino effect of issues that we have to fix. So the first immediate issue is that in order to get correctness, we must provide openings for this commitment, and there are going to be n openings, one for each user, and so that means we have no succinctness anymore. So that's basically trivializes the construction. And so our current workaround is to take basically the randomness for this commitment and openings from the random oracle applied to the aggregation query. And so now basically, at least we have a way to get small ciphertexts, but even now it's not really clear what we can actually do with this commitment since the randomness is all in the clear. So like what can we actually do without the adversary noticing? Well, the idea is the following. Basically, if we sample the commitment from a nice distribution, what we can do is actually kind of explain the randomness. And what that means is like given a sample, we can output a random string that sort of looks correct. And has the right distribution. And what this will allow us to do is program C0 in such a way that we can do sort of the similar trick as before, where now we can derive this term from S times A. However, in doing this, we have now introduced one last problem that we need to deal with, which is these openings, because we have to simulate both the commitment and the openings if we want to, if we want to simulate the full challenge ciphertext. And so this is where those DI vectors are going to come in and save the day. Basically, if we make these openings high enough norm, so from some sort of like high norm Gaussian, what we can do is kind of inject D into the opening relation for C0 in such a way that we can then program DI equal to A times KI, where KI is like large norm and matches the norm of Z0I, and then this can sort of like smudge out this alternate path that we took in some sense. And yeah, that's basically the idea of the proof, and these techniques will also work for adaptively secure DBE in the random oracle model. So that's where that result comes from. So I'll conclude with some open problems. The first is proving security from the plain LWE assumption, which would be great, but seems very difficult, even if we are allowed random oracles. Something maybe a little more achievable is trying to remove the random oracle from either of these constructions. But this too, I mean, the current security proof relies very heavily on this random oracle technique. So it's not too clear how to actually do this. And then lastly, it'd be nice to get more cryptanalysis and applications of these new lattice assumptions like succinct and decomposed LWE. And with that, I'll end my talk.
Thank you, Jeffrey, for the talk. Any questions?
Thank you for your talk. My question is like about the registered AB in the like last slide. So like, is it correct that the construction relies on random arc array? One more previous slide. So is it correct that the construction relies on random arc because like challenger want to program the like commitment Caesar depending on the given CO provided by the adversary?
Yeah. Basically, the random oracle is needed so that we can kind of like compress this this like cancellation trick in a way. That's what you're asking.
Thank you.
I also have a quick clarification question. So is random oracle also needed for the DB construction in the WW paper?
So the random oracle is not needed if we only care about selective security. So there, with selective security, basically we can do this re-randomization trick, but we can program it into the public parameters. And so we don't need any of the random oracle stuff anymore.
I see.
Because it's only because we're doing this at encryption time that we have to like generate the openings on the fly and stuff.
Nice. Makes sense. Thank you. Any other questions? Okay, then we will end early and we're off to lunch.